Hello everyone again, and welcome to my channel, the Dajo Mirrors channel, where we're going to dive into a specific word problem involving a physics particular topic, which is electric fields and magnetic fields, and we're going to apply this to a particular object, which in this case are electrons. And first, this question deals with a magnetron in a microwave oven, and this actually emits electromagnetic wave. Now, this electromagnetic wave has a frequency of around 2450 megahertz, which is units for frequency, megahertz, or I would say hertz. Now, the question asks that what magnetic field strength, which is actually labeled as B, is required for the electrons to move in a circular path with the frequency, with that same frequency, which is what we have right here. So now, since this question is asking for the magnetic field strength, we need to go back to this particular question which talks about a circular path. And to accomplish a circular path, we need to be able to figure out that, hey, first there is a trajectory of the electrons, and this trajectory of the electrons, which states that it's a circular path, actually requires an angular frequency. So to determine the angular frequency, we multiply 2 by pi and with the frequency that is given. So as a result, what we get is 2 times pi. Pi we know is 3.14, and this is multiplied by 2450 megahertz. We can actually determine our value by punching it into your calculator, and we get around 15,393.804 radios per second. So once we're able to accomplish this angular frequency, and this particular strategy is to be able to work within the circular path and how that reflects on the relationship with the magnetic field. So what we know from our Newton's second law of motion is that the net force, which is a product of the mass of that particle and the acceleration of the particle, is equal to the combination of the electric field and that of the magnetic field, which is the combination of the velocity with the cross product of the magnetic field. So the force in there of the electric and the magnetic gives us the net force. Now we know that electricity is not involved in this particular question. We're going to be focusing on the net force, which is pretty much equal to that of the magnetic force. So in this particular case, what we're able to figure out is that where our acceleration is actually, since it's centripetal acceleration, because it's actually in a specific condition, which is a circular path, we actually go with the square of the velocity divided by the radius of that particular circular path. So if we put this in this particular equation where this equals to 0, then what we arrive at is that our mass multiplied by the velocity, or squared divided by r, is equal to the quantity of charge times the velocity times the magnetic field. Now we know that we have velocities on both sides, then it means that our magnetic field is equal to the mass times the velocity over the quantity of charge times r. Now, since we know that in this case we need to introduce our angular frequency, which is labeled this, we know that this omega, small omega sign, is actually equal to the velocity divided by that of the radius. So in this case, to solve for the radius, we actually know that in this case the velocity is divided by angular frequency. So in this case we substitute that in here and we actually determine our particular expression in terms of the angular frequency. So v over the angular frequency is equal to the mass times the velocity divided by the quantity of charge times the magnetic field. So as a result, in this case we know that velocity cancels out velocity, and what we get is an expression that actually expresses the angular frequency with that of the quantity of charge and the magnetic field, and also considering the mass of the electron. And this particular expression actually tells us that the angular frequency is not dependent on the particle's velocity and that of the radius of the path. So as a result, once we know that the mass of the electron, which we know is a constant, is 9.11 times 10 to the negative 31 kilograms, and we know that the magnetic field is what we are determining, which is measured in Tesla, and then we know that the quantity of charge, which is in the units of the coulomb per electron, which is 1.6 times 10 to the negative 90 coulomb charge per electron. To determine our magnetic field, in this case we know that our angular frequency is determined above 15,393. So in here we have 15,393 point, in this case 804 radius per second. And once we put those into this equation, what we have to determine our magnetic field is multiply your angular frequency by the mass, and then you divide it by the quantity of charge. So in this case we have 9.11 times 10 to the negative 31 kilograms for the mass of the electron times that of the angular frequency, which is 15,393.804 radius per second, and then this is divided by the quantity of charge, which is 1.6 times 10 to the negative 19 coulomb per electron. And what we get as our final answer is equals to 0.087 Tesla. So this is actually the magnetic field strength that is required for our electron to move at a specific frequency, which is what we have right here in a circular path. So that's about it for this particular video. Hope you're able to understand the mental strategy involved in approaching this question. Hit a comment down below, let me hear your thoughts. Hit the like, share and subscribe. By that way I can talk to you later. Stay smart and believe in yourselves.